Welcome to this episode of Real Chemistry. I am, as always, Dr. Morris, and today what we're going to be doing is calculating the energy and hence the wavelength of a photon that would be absorbed when you excite a dye. And we're going to do this using the particle in the box model. So the whole question is, let's say I have some dye, like this guy down here. This turns out to be 1,4-diphenyl 1,3-butadiene. And I want to know if I put that on a UV vis, what's going to be the maximum wavelength of absorption, or lambda max. Where's this peak going to be? It may be a little surprising, but you can actually use the particle in the box model to do this. Let's talk about why. Well, basically, the particle in the box model tells us that we have a well where our electron can freely roam around. That's where the potential is zero. It also says we have these barriers that the electron can't get into. It turns out our dye is pretty similar to that. We have a conjugated pi network here. That means our pi electrons are delocalized, free to roam around. And so those electrons have a potential that's very low. And then there's a wall right here that they can't get through. So our dye actually looks a bit like a particle in the box model. And it turns out you can get surprisingly accurate predictions of what lambda max will be by applying the particle in the box model. How are we going to do that? Here's the 5 steps that we're going to use. Now, importantly, what we ultimately want to do is calculate the energy that our electrons can be at in this pi network and think about how much energy it's going to take to transition them from one energy to another. And that'll tell us what wavelength photon we need. So we're going to need to determine n. And n turns out to be related to how many delocalized electrons we have in our pi network. We're going to need L, which is the length of our chain, which we can calculate. And then mass in this case is just going to be the mass of the electron. So we already basically have that. So let's start off with this first step here, which is determine the number of delocalized electrons. Well, the number of delocalized electrons is just given by how many pi bonds we have times 2. So I have 1 pi bond, 2 pi bonds, 2 pi bonds. Those are the only pi electrons in this system. And that means that even though there's other electrons around, they're not delocalized. They're not free to roam. They're associated with a given atom. So 2 pi bonds, 2 electrons per bond, gives me 4 total pi electrons. And that's how many electrons are free to roam through this whole network. The other ones are associated with an individual atom. They're not free. They're not being modeled as being in our box. So we have 4 pi electrons. That's the first thing we got to do. Just count the number of double bonds, multiply by 2. Now we want to determine the length of our conjugated chain. So all we have to do here is take into account the carbon-carbon double bond and single bond length, and how many of each type we have. So let's go ahead and do that. We have 2 double bonds, just as we saw before. So we need to do 2 times the length of a double bond, which is 133 picometers. That's going to give me 266 picometers. Then what we need to do is calculate our single bonds. 1, 2, 3 single bonds, so 3 times 154 is going to give us 462 picometers. So that's separately calculating our double bond and single bond. And then we need to add them up. That's going to give us 728 picometers. Really, though, when we plug everything into our equation, we need SI units. We need kilograms, meters, joules. And that means that what we're going to need to do is convert this to meters. And that just means we take 728, multiply it by 10 to the minus 12th, and that's going to give us meters. So that's the length of our conjugated chain. Now, you'll notice that I've been adding our answers to our questions. So I have 4 electrons and a 728 times 10 to the minus 12th meter chain. Okay, so how am I going to get this n? I want to calculate the energy of our highest occupied molecular orbital. How do I know what that is? Well, this is where the number of electrons is really critical. I have 4 electrons, and I have this energy diagram here where I've laid out the different energy levels. And I'm going to fill up these energy levels with my pi electrons just like I would in an electron configuration in GenChem. Each level can hold 2 electrons. So in my n equals 1 level, I have 1, 2 electrons. And my n equals 2 level, I have 1, 2 electrons. That's it. Those are my 4 electrons. So my highest occupied molecular orbital is the n equals 2 state. My lowest unoccupied orbital is n equals 3. And that means I can go ahead and calculate the energy of each of my states. So the energy of my second state, that is my highest occupied molecular orbital, is equal to h bar squared. I wrote the value down there. I'm not actually going to plug in the number because it would be too tedious, but all I'm doing is plugging in the value for h bar squared into my calculator. And now n squared, which is going to be 2 in this case, times pi squared. Again, I'll put that on my calculator, but not write it out here. Then that's over 2 times the mass of the electron, which I wrote down here, 9.11 times 10 to the minus 31 kilograms. You need to plug that in kilograms, just keeping with SI units. And then I need to plug in my length squared. That's what I calculated previously, 728 times 10 to the minus 12th meters, and that's squared. So when I calculate the energy of my highest occupied orbital, it has an n equal to 2, and the energy is going to be 4.54 times 10 to the minus 19th, and the units here are going to be joules. You should get something on the order of 10 to the minus 19th, 10 to the minus 18th. Much bigger or much smaller than that, and you probably made an error. So it's not uncommon to screw something up and get out 10 to the minus 30, or to screw something up and get out 10 to the minus 10. Those are both ridiculously high or low. You want something right around an electron volt in terms of energy, which is a 10 to the minus 19th. All right, so I'm going to write down and record the energy of my highest occupied molecular orbital. And in the next step, I'm going to calculate the energy of my lowest unoccupied molecular orbital, which is n equals 3. So my LUMO is for n equals 3. And the same calculation here, I still have h bar squared. N squared this time is going to be 3 squared. And then pi squared over 2 times the mass of the electron. And once again, the length of my chain, 728 times 10 to the minus 12th meters. And that's got to be squared. Don't forget that. So the energy of my third level is going to be 1.02 times 10 to the minus 18th joules. Again, on the same order of magnitude, but bigger than my second energy level. And that's another good checking point. As you go higher on this graph, n equals 3, n equals 4, n equals 5, your numbers should get bigger. Okay, now I want to calculate the wavelength of my photon. Critically here, I've blown up this energy diagram so we can see what's going on. What I want to do is I want to take an electron from my highest occupied molecular orbital, and I want to kick it up to my lowest unoccupied molecular orbital. And I'm going to do that with a photon. And that's going to have some wavelength. So I need to give exactly enough energy to kick that electron up from n equals 2 to n equals 3. And that's the transition you'll see as your peak in your UV visible spectrum. So what I really care about is the distance between the second and third level. I don't care about the absolute energy levels about them, I care about the difference. It's like how much energy do you need to go upstairs? I don't care about the energy that I have at the bottom and the top. What I care about is how much I have to change. And so I care about delta E. In this case, delta E is going to be equal to E3, the final state, minus E2, the initial state. And delta E turns out to be 5.67 times 10 to the minus 19th joules. That's also the energy of my photon. The energy my photon needs is exactly equal to the change in energy, the difference in energy between those two steps. And now I'm ready to use my calculation, or my formula over here, energy of photon is equal to hc over lambda, to calculate lambda. So energy of photon equals to hc over lambda. With a little algebra, I multiply both sides by lambda and divide both sides by the energy of my photon. I get that guy. And again, I've spelled out Planck's constant. In this case, the h is not h bar. So it's 6.626 times 10 to the minus 34, and the speed of light. So we plug in hc and we divide that by my difference, which is 5.67 times 10 to the minus 19th. And what I'm going to get for my wavelength is 3.50 times 10 to the minus 7 meters. Well, you're used to seeing those numbers in nanometers. So if I multiply that by 10 to the 9th to get nanometers, you're going to see that's 350 nanometers, which would appear in your UV visible spectrum. That's the lambda max. That's where your dye is going to absorb. So what we've done is we've modeled 1,4-diphenyl-1,3-butadiene as a particle in the box for this conjugated chain. And we've predicted the lambda max to be 350 nanometers. That turns out to be maybe 10 nanometers away from the actual correct value. So the particle in the box can give you surprisingly close values for some dyes. Thank you for watching this episode of Real Chemistry. As always, click on that icon below to subscribe. You can ask any questions you have below. Please visit my channel to see more videos. Thanks for watching.